Thank you, everybody, for attending this last session. The session after the previous one. And the reason I say that is because the previous one was talking about the monetization of oil and gas fields. Well, one of the key ways of doing that is, of course, innovations in development. And more than 70% of operational fields globally are now beyond design life. And so the maturation and the prolongation of operations in mature fields is going to be important. One of the best ways to do that is through innovation. But innovations are also very important for de-risking and reducing the costs and improving operational performance for greenfield projects and developments as well. So I'm Harvey Johnstone. I'm the Director for Environment and Asia Pacific for the International Association of Oil and Gas Producers. We're a membership made up of 97 companies. Our members produce about 45% of global oil and gas production output. So we have 4 very good presentations today, which is all built around different themes of innovation. And to start it off, I'm going to invite Vishesh Pushkar, who is the CGM for Chemistry, Oil and Natural Gas Corporation Limited. Vishesh has a Master of Science Organic Chemistry, and he's been with ONGC for 34 years. I'm just going to do very brief introductions for the speakers, so I would encourage you to go and look at the bios followed through in the app so you can get a better appreciation of the speakers. So Vishesh is going to talk to us today about eco and environmental friendly next generation fracturing fluid using produced water. So Vishesh.
Thank you, sir. Before starting my presentation, I would like to thank my higher management for giving the opportunity to present this paper. Actually, everybody knows this water scarcity is a basically major problem due to the ongoing population growth and all the things. I think by 2050, the population will be very high in India, around 1.6 billion. So definitely this is our responsibility to save the groundwater as much as possible. ONGC is making too much positive efforts to save the groundwater. How we can save the groundwater? Actually, it is very imperative to preserve it for further human consumption and the agriculture also, because the groundwater is very, very important. It required for the agriculture purpose also, and human consumption is also very much, need the water. So definitely only 2%, 3% water is available, drinkable water, so that we have to preserve as much as possible. So we are making the effort for this thing. So WSS has carried, actually WSS is involved in hydrofracturing jobs. So definitely a lot of produced water is coming from the formations. We wanted to, this water is being treated with the different types of the chemicals and through the mechanical as well as the chemical process, and to make it usable for basically water injection wells and the disposal well also. So this water, I think in Ahmedabad itself, around more than 50 to 60% produced water is coming along with the basically oil and gas. Even in Mehsana also around 90% water is there. So that means a lot of produced water is available which need to be treated. Otherwise, it will be very difficult to dispose it of this water. So scarcity of the basically groundwater, it not only basically it gives impact on the basically health of the basically human beings as well as animals also. So my topic is basically to designing a new gen frac fluid of hydrofracturing frac fluid using produced water. So this topic will cover around 4 or 5 points. This will cover. One is water scarcity, globally. I will talk about how the water is basically getting scarcity and how we can address all these situations. And the use of produced water, how we can use this produced water, what are the treatment we require to make it usable for our operation. That part we have to see it. And the elemental analysis of this produced water, how this water is basically differ from the technical water what we are using right now. So that chemical analysis, we have already done it. And with this fluid water, we have used fraction fluid. We have designed the fraction fluid, and what are the chemical we have added to fraction fluid, because the fraction fluid is a basically basic fluid which is very much helpful to carry the desired concentration of sand into the formation. As you know, hydrofracturing is basically a very complex operation where we are fracturing the formations just to get the oil from the formation. So definitely, if suppose you are putting something, if you are fracking the formation, so you are carrying the desired concentration of the sand into it and placing the sand just to make the porous, permeable and permeable. Okay. So definitely this, if suppose you want to place the more sand into it, definitely it requires some carrier fluid. That carrier fluid is called as fraction fluid. So we have tried to use this fluid, prepare this fluid using this produced water. Yeah. If you see the basically graphs, actually in population growth, this water scarcity, why this water scarcity is coming? Actually due to the population growth, and the climatic change is also there. It is responsible for it. There is a need of the agriculture demand also, and lot of urbanization is taking place. That's why the huge water is required. So this is all moral responsibility to save our formation water so that it can be used for the drinkable purpose of the human consumption also. This is the basically produced water, around 10,000 cubic meter water every day it is being produced from the western region. What we are doing it actually, this water is getting accumulated at the ETP, and that water is being used for the water injection, effluent disposal, and the drilling purpose and the stimulation purpose. In the drilling, we can also design drilling fluid, suitable drilling fluid using this produced water. But right now we have tried to make full effort to design a good hydrofracturing fluid which can be used for the stimulation purpose. Stimulations, if you see the application of this fluid in the stimulation hydrofracturing, it can be used. It can be used in the acid addition job also. We are doing a lot of acid stimulation where we can use the produced water. And the gravel for pack operations, we are also doing it where we require high viscous fluid which can be also prepared with this water. And the CTU, when we are lowering the CTU just to clean the well, so definitely you require some viscous fluid. That fluid can also be prepared with this water. And other jobs we are also doing it. Fracture fluid, if you see the fracture fluid study, we have also carried out fracture fluid study. First what we have done actually, we have done the water analysis and we see how this water is differ from the technical water and how it can be usable for the fracture fluid, how it can be suitable for the fracture fluid. Then we have observed the gelacing tendency of the fluid. We have prepared fraction fluid, some with the desired viscosity around 0.4 gelling agent we are putting into it. We achieve the viscosity around 25 to 30 viscosity. After that, we are making this fluid by using the good cross-linker. We are making the viscosity around multiple folds. Okay, so that fluid become cross-link fluid, which help to carry the desired concentration of the sand into the reservoir. So this is the basically basic structure of this thing. And how this viscosity is basically whether the viscosity is stable at the particular temperature or not. So we are measuring the viscosity also with the STHP viscometer. We have a STHP viscometer, so we can see the this fluid, whether this fluid is stable or not. Because if the fluid is not stable, then it will not carry the desired concentration of sand. There is another experiment what we are doing over here, propellant settling. We are putting around 4 to 5% propellant into it and then see whether the propellant is getting settled or not. If the viscosity is not sufficient, definitely the propellant will start settling over there. So there may be chances of job failure. That's why we need a consistent viscosity which is required to carry the desired concentration of sand. Once we have placed the basically viscous fluid into it, so definitely we have to break this fluid also. If the fluid is not break, so definitely after placing the basically propellant, then fruit should be broken completely so that the fruit can come out and the propellant will remain inside the formation. So that's why breaking study is required. So we add some chemical which help to breaking the basically breaking study. And one more important experiment we are doing it, core flow study. Because if you are putting the water, and naturally hydrofracturing fluid is prepared with almost 90% water is there, 95% water is there, rest of the chemicals are present. Definitely this water when comes in contact with the formation, there may be chances of getting swell also. Because this water contains divalent compound also, and calcium, magnesium, all the things, so definitely they may create little bit hindrance also. So definitely when this fluid, we basically flow through the core flow and see whether it is soluble or not. And we are putting one shell inhibitor also into it, that is a clay inhibitor, or the polyamine recently we have introduced. Polyamine we are also using, which act as a shell inhibitor, which arrests the basically clay swelling properties. If you see the source of produced water, actually, we have collected this produced water from different ETP. In ONGC, Ahmedabad has so many ETPs, Jalora ETP, Limbodra ETP, Navagaon ETP, Kalol, and the Kalol ETP too. So we have collected the water from there, and we have done the elemental analysis. Accordingly, we made the treatment to make this water usable for it. You see, these are the basically parameters which need to be checked in the produced water. One is turbidity. If the turbidity is very high, so definitely, because we are putting this fluid into the reservoir, the reservoir may be, damaged. So turbidity, if the higher turbidity is there, so it may be detrimental to the reservoir also. So turbidity we need to arrest. And the bicarbonate, magnesium, ions, sulfate, these are the basically ions available into it. So we have to give the treatment, the sequestering agent and other chemical we have to put it. Even the Na also we have to put it. Chloride, calcium and pH. pH is also very, very important. If the pH is not there, so that we will not be able to design the good process. All these parameters actually with what we have collected from the different sources, the ETP water. So you have seen there are some parameters actually which are in bold actually. So these limits are basically higher side. These are the basically not permissible limit. So we have given the sufficient treatment. We have done some mechanical process also, filtered this fluid to bring down all the basically TDS, TSS particles also. And we have given some treatment, sequestering agents, we have put it over there, demulsifier, Na also we have put it over there, and we make the water usable for it. So what we have done actually, because there are some foreign material present in the basically ETP water, produced water, so definitely we pass this 200 mass filtration size, so we remove the basically all foreign particles, because since the pH of this fluid is more, so we add some acetic acid to bring down the pH. There may be issue of the basically deformer, because the polymerization, due to the polymerization, there may be chances of the forming also. So what we have done, we have added one special chemical, that is a deformer, which can, remove the basically bubble formation. And we have checked the turbidity and the pH and bicarbonate also. Just in this formulation, we have designed 3 formulations using gelling agent, 0.3% gelling agent, which obtained around 25 viscosity, and 0.4%, which is having around 33 viscosity, and 0.4%, 5%, 41.6%. So this viscosity, actually, we are using the different concentration of the gelling agent depending on the reservoir temperature also. Because if the temperature is more, so definitely at the higher temperature, the viscosity goes down, and your close-linking fluid will not remain stable. So that's why we have to sometimes add the more concentration of the gelling agent. So what we have done actually, technical water with the 0.06% BA and the 2% KCl. But we have added this thing, so we have seen this viscosity is coming. And the produced water, when we have added this chemical, the viscosity has gone down, because a lot of divalent compounds are there which are creating a lot of hindrance over there. So that's why this kind of treatment is very much required. Then this water may be useful for it. Then what we have done, we have added acetic acid and the 0.6% bactericide is already there, and the deformer. Again the viscosity has come around to 18 to 31, as we have seen in the technical water. It means if suppose you are adding the acetic acid, so definitely this water is almost equivalent by mechanical and the chemical process, it will be almost equivalent to technical water, so you can get the same viscosity over there. This viscosity, now what we have to do it, actually this viscosity is on a linear gel viscosity. What you have to do it, you have to cross-link the fluid. Unless until you will not cross-link, the viscosity will not go high and propellant will not carry into the formation. So what we have done actually, we have cross-linked this fluid and checked the viscosity rheological profile in the basically what you call in SPSP viscometer. So what we have seen at 70-degree temperature, where the viscosity was coming around 690 cp. Minimum viscosity we require around at 70 degrees centigrade 300, but it is 690 is coming. That means the fluid what we have prepared there, it is very much stable and which helps to carry the sand into it. Propellant settling we have also observed. Initially, this was the propellant settling, and after 20 minutes and 90 degrees centigrade we have kept it. There is no problem with the basically propellant. The propellant is not getting settling. It means our fluid is completely stable. After this, what we have added actually, we have added the breaker, and once we have added the breaker over there, so definitely the complex gel completely broken, and this fluid will comes out from the formation, leaving the propellant inside it. This is the core flow study. We have made the comparison with the technical water as well as the produced water. We have added these chemical and we see there is no change at least. Same core flow study there is called the permeability, porosity and permeability remains intact. There is no problem. This is the broken gel. These are the parameters which we have checked. Gelling agent 0.4%. These are the basically composition. We are putting clay stabilizer, bactericide, defoamer also acetic acid. Now these are the basically chemical which we have added and make this water usable to as a complex fluid. This water we have used in 2 wells. We have done the fracturing, successful fracturing has been taken place, well A and well B, and it has given excellent result, and the production is also very high as compared to this thing. You see the production, initially in the A well, there was 0 production, and after this HF job, it came to 2.5, and in another well actually it was 0 and it came to 10. So production is also increased, there is no problem with the permeability is okay. So this water can be usable for the hydrofracturing purpose. These are the basically takeaway I would say. Okay, if suppose use this thing, so definitely 75 to 1 lakh cubic meter water we can save it. This water is very, very much useful, and if suppose you save this water, you can reduce the maintenance dose of this chemical also, and the cost is also, you can reduce the cost also. Thank you very much. This is all about my presentation.
Thank you, Vishesh. Next up, I want to invite Mr. Dicky Alviansyah. He's an application engineer for electric submersible pumps within the production solutions business at Baker Hughes. And Dicky's going to talk to us about unlocking operational excellence in power-constrained offshore fields using advanced ESP optimization. So Dicky, please.
Okay, so good afternoon, everyone. It's an honor to be here presenting at India Energy Week 2026. My name is Dicky Alviansyah, an application engineer at Baker Hughes, and today I'll share how we have unlocked the operational excellence in power-constrained fields through advanced ESP optimization with PMM, or permanent magnet motors, with smart edge real-time monitoring technology implemented in Indonesia's offshore field with the biggest ESP population. So I'm just going to start the presentation with the introduction, and then we move on to the methodology to propose the solution accordingly. And then I'm going to briefly explain about the technology overview, and then we're going to deep dive into the results and discussion, and I'll end the presentation with the conclusion. So the ESP have been widely used, particularly in the offshore Southeast Sumatra field, because it is considered to be the most suitable artificial lift due to its operational target, and then the power generation, and also the infrastructure establishment. And the field itself is divided into 3 areas, but in the study we're only focusing on the north area, which have 90 wells produced using ESP and powered by gas turbines with the fixed capacity of around 22 megawatt. And having said that, the power constraint forces well prioritization, where the operator have to shut in many wells despite their potential, or even sometimes swap power between one well with another, which then restricts the oil production. And in terms of surface piping, it limits the maximum rate per well to only 14,500 barrel feet per day, with the water cut in most wells reaching up to more than 99%, making them economically unattractive under induction motor technology. Because as we know that induction motor requires what we call as slip to generate the rotor magnetic field, which results in lower efficiency and increased power consumption. So solving this challenge, it will be so beneficial for the operator, especially in the north area, because it can better the production targets and also the economic performance. So to address the challenge, we applied a systematic framework based on the technical, economic, and operational aspects to ensure feasibility and maximize efficiency. From the technical aspects, there are power consumption of IM systems, target run life, and power intensity, or how much power is required to lift each barrel of fluid per day. And then from the economic aspects, we have IM rental charge and the oil potential that must be considered. And lastly, from the operational aspects, being the most critical, because the PMM will require what we call as variable speed drive, or the VSD as the motor controller, include with the transformer, so ensuring that the platform has sufficient space is very important. And the second one is that we have got to ensure that the well is not water out condition, or 100% water cut. And by combining these 3 aspects, then we can rank all of the wells, and then in the study, we selected 4 wells to be applied this solution. So what we do is we deploy high efficiency permanent magnet motors to reduce energy losses and integrated them with smart edge real-time monitoring technology, offering 24/7 surveillance and remote control capability. So what makes the PMM different? Well, the PMM, or the permanent magnet motor, has embedded magnet into the rotor, so no slip is required to generate the rotor magnetic field, which will result in higher efficiency and decrease the system power consumption by 20%. And also it lowers the idle amps, enabling better control at lower loads. The PMM also offers higher power density, which means that it can achieve higher horsepower with the same motor length, or the other way, the same horsepower can be achieved with shorter length of PMM, allowing us to set the ESP even closer to the perforation in deviated wellbore, which is very critical, especially in mature fields where the reservoir pressure has been so low. And the PMM keeps the power factor and efficiency at optimal level over entire load range. And lastly, the PMM delivers higher power factor, which means that it can help reduce the power system size requirements and also cable power losses by 25%. And the other one is the real-time monitoring system, which provides transmission, visualization, and monitoring of ESP data to optimize production by monitoring some key parameters such as system status and safety limits, system performance, and power data. And the technology also offers what we call as remote adjustment capabilities, allowing proactive optimization to start or stop the well remotely, or even preventing shutdown in the first place. And this capability significantly minimizes HSE risk because no on-site visit is required to just adjusting the frequency. because no personnel are exposed to the risk, especially in offshore conditions during bad weather, and it can also lower the operational expenditure. And by preventing shutdown in the first place, we can then maximize equipment run life and also ensuring production continuity. And these are the data of the wells that we have selected through assessing through comprehensive methodology as explained earlier. So basically all the wells have similar characteristics, with water cut reaching up to more than 99%, and then 32 API of oil, and the target rate of 14,500 barrel feet per day, except for the A7, it's only 10,000 barrel feet per day. The rest relevant data can be seen in the table. So here is the comparison of power consumption between the IM and the PMM system. So across these 4 wells, we can see that the power consumption across these 4 wells are lower compared to the IM systems because the PMM have higher efficiency. Now the question is, why the power saving is different between one well with another? So the variations in power saving among these wells is influenced by so many operating factors, such as the nameplate horsepower of the motor that we use, and then the production rate, and one of the most critical is being the motor loading percentage as observed in the study. So all IM systems in the green bars there operate above their rated capacity, ranging from 108 to 113%, which is actually not a very ideal application. And on the other hand, the PMM shows more optimized motor loading between 90 to 98%, which is ideal for efficiency and reliability. So let's take a look one by one. NC20 achieved the highest efficiency up to 27%. Why? Because the nameplate horsepower of PMM is significantly lower compared to the IM system, that is from 466 to 425 horsepower. And then this well also has the highest or the most significant motor loading reduction from 113% to 90%. And then for NC19, achieved the most realistic, if I say, improvement of 13% of power saving, because the nameplate horsepower is somehow quite similar between the IM and the currently the PMM system. But again, the power saving can be achieved because the motor loading reduction from 108 to 92.3%. And then for the N11, it achieved modest efficiency improvement, leading to 9.15% of power saving. But one interesting point here is that even though the PMM horsepower was slightly higher compared to the previous IM system, from 386 to 425 horsepower, power saving can still be obtained because of the reduction of motor loading percentage from 112 to 92%. That's why it is concluded that the motor loading percentage plays significant role in determining the potential of power saving. And A7 achieved the smallest power saving of 8.8% because it has the lowest target rate, that is only 10,000 barrel feet per day. But still, the PMM performed better in terms of power consumptions in these all wells. And we can calculate that the average power saving across these 4 wells is 14.6%, reducing the total power consumption from 1,396 kilowatt to 1,185 kilowatt, or a saving of 211 kilowatt. And this saving is estimated to give the operator power cost saving around $200,000 annually. And decision to use 425 horsepower PMM for all wells was driven by logistical concern to simplify the inventory management and also to accelerate deployments, because by enabling faster deployment while at the same time maintaining optimal motor sizing, then PMM logistics can act as a key enabler for scalable energy optimization across power-constrained offshore assets. We have discussed about the PMM advantages, how it can save power, but the true value is unlocked when it is integrated with smart edge real-time monitoring. And this integration brings the ESP optimization to the next level. So the system will continuously track various important parameters such as temperature, vibrations, pressure, and then power consumption, which can then be used to assess pump performance by comparing the design data with the actual data, or what we call as matching. And then from that assessment, we can then adjust the frequency remotely if required. For example, this is a real example of optimization. So N11 well, one of the wells that we have in the study, was producing at 13,840 barrel feet per day at 105 hertz with 270 psi of tubing pressure. So as can be seen here, after we have done the matching, it was found that the SP was operating slightly in upthrust condition, risking pump stage wear and reduced lift efficiency and increasing power consumption. So the operator can take data-driven action to adjust the tubing pressure and also remotely fine-tune the frequency using real-time monitoring. This is where the real-time monitoring, this is where the optimization took place. I cannot, okay. So now currently the well is now producing within the recommended operating range at 13,520 barrel feet per day at 107 hertz with 350 psi of tubing pressure, ensuring optimal performance and equipment protection. Additionally, lower power consumption was observed due to higher efficiency. So what can we conclude from the study is that the integration of the permanent magnet motors with smart edge real-time monitoring marks a significant advancement in offshore field development, where a clear indication from our study in offshore Southeast Sumatra field, it shows benefit 211 kilowatt reduction in power consumption across 4 wells as a result of 14.6% improvement in energy efficiency and an estimated around $200,000 in annual power cost savings. And the real-time monitoring system proved its essential in unlocking the full value of PMMs by enabling dynamic control, early fault detection, and remote adjustment. And this approach represents a strategic shift in field development philosophy, which offers a scalable and replicable solution for optimizing operations in other fields facing the same issues such as power constraint or aiming for the same goals such as ensuring production continuity. And hopefully the key points I've shared today are useful, and I'm happy to discuss it with you further after the session. Thank you very much.
Thank you, Dicky. Next, we have Mr. Gabriel Gil. Gabriel received a bachelor's degree in geophysical engineering from the Simon Bolivar University in Caracas, Venezuela, and he has a master's science degree in geophysics at the University of Houston. And today, Gabriel is going to talk to us about the application of spectral attributes in carbonate reservoir characterization. Thanks, Gabriel.
Well, good afternoon, everyone. Thanks for the opportunity to be here, and thank you for being present for this session on the stage. As Harvey mentioned, I'm going to be talking about the application of spectral attributes in carbonate reservoir characterization using machine learning to produce seismic volumes of effective porosity. Okay, I want to start with the motivation of this work. First of all, as you have seen in many presentations during the day, machine learning has been talked about a lot. Okay, so yes, machine learning is a process that has been used widely in the industry, not only in geophysics, but in general in different applications. And one of those applications in the geophysical part is the estimation or prediction of seismic property volumes. Okay? So with that in mind, I'm going to show the benefits of including a special type of seismic attributes, which are spectral attributes, in the prediction process, and show how those help improving the resolution and reducing the error in the prediction, or improving the prediction accuracy. And I'm going to be demonstrating this on a data set where the objective is the prediction of effective porosity on a series of carbonate layers from the Pennsylvania and Mississippian age. The average thickness of the target column is about 450 meters. Average porosity is in the order of 8%. There are tight carbonates in that column. There is also carbonates with higher porosity values. And most of the porosity intervals are actually happening in sequences of 6 to 20 meters approximately. It is a carbonate platform, so it is expected geologically to have some lateral continuity of those porosity zones, but it's also expected to find vertical and lateral discontinuities or heterogeneities on the presence of the carbonates, the porosity in the carbonates. Some comments on the machine learning process that was used for this particular work is it's not a deep learning process or a full AI. It's more like a relatively shallow machine learning process. It is a supervised process because we're going to be using well data, well logs, to guide the prediction process. Okay? Mathematically speaking, there is a formulation for it. It's the L0 standard, which is calculated as the error between the actual logs and the prediction result of the well locations. We try to minimize that difference. So again, that means we are doing a better prediction. And we're going to use that in this particular case to predict effective porosity as a seismic 3D volume. The minimization of this function, so the reduction of the error in the prediction is used, how it's done using the minimum support algorithm. That's preferred over other conventional optimization approaches because it helps achieving the optimum solution faster and also minimizes the number of elements that go into the prediction, which is, for statistical approaches, is important. The final result is actually a combination of different seismic attributes. Each one of those seismic attributes has an operator applied to them. Okay? And the size, that operator is actually calculated by the prediction process during the training, and the size and the length and the shape of those operators are actually individual for each one of those seismic attributes that the process selects. Okay? We just input a database of attributes, and the process selects the most useful from that. Also, a feature from the algorithm is the minimum support. It helps automatically to reduce or discard attributes that are highly cross-correlated between each other, so there is redundant information if you use many of those. So it will find which one of those to use, and that way, again, reduces redundancy and improve the information content of the final result. So to demonstrate the benefit of adding those spectral attributes in the prediction process, I'm going to be using two workflows, one simple, another one a little bit more advanced. The simple one, we start with the seismic data. We do the proper well calibration. There are 5 wells in this data set. And from there, we do a pre-stack elastic inversion to get elastic attributes. And those elastic attributes with the seismic stacks and some additional amplitude-based attributes is what makes the attribute dictionary that is used in the machine learning process to create a porosity volume. Now, parallel to that, we also implemented this more advanced workflow where we start with the same data set, with the same well calibrations, but we do a data cleaning. Okay, that data cleaning is meant to improve the quality of the seismic data while preserving the responses in the seismic. Then the sparse layer inversion process, there is a process that on its own has a spectral analysis internally. It is normally used to enhance the resolution of the seismic, so will let us see finer events, better stratigraphic information. In this case, was actually used to correct for variations in image content in the seismic data. So with those clean and balanced seismic volumes, we rerun the pre-stack inversion to produce a new set of elastic attributes. And also for the seismic data, we calculated the spectral attributes. Okay? And those spectral attributes are part from spectral decomposition, and we output a variety of isofrequency volumes, including amplitude, magnitude, and phase. And we also run a different decomposition method called phase decomposition that breaks the data into phase components, and those phase components can be related to layer responses present in the subsurface. Okay, all this from the seismic data. Now, with that extended attribute dictionary, the optimized stacks, the new set of elastic attributes, the spectral attributes, we put all that together as a new attribute dictionary to run the prediction process again. For the prediction for both workflows, the parameterization, the windows of analysis was actually consistent. The main difference was the attribute dictionary that went into both prediction process to show a fair comparison of the prediction quality from both approaches. Looking at the QC display for the prediction process on the conventional workflow, okay, only seismic and inversion, the black curves in here are the actual porosity logs from the wells, and the red curves are the prediction results at the well locations. You can see there is an overall match between the shape and the red and the black curve. However, in several cases, the red curve fails to estimate the very low porosity zones as well as some of the high porosity zones. If you look at well number 2, if you look at well number 2, you'll see that there are thinner high porosity zones that are actually not captured by the prediction results. This prediction gives a correlation coefficient of 73% that you see on the top. And look at the QC of the spectrum of the data. It's limited based on the bandwidth of the input seismic data. Letting us see probably something 35 to 40 meters layers in there, and we know we are below that. Cross-plotting a couple of wells between the actual logs and the prediction result, we see well number 5, we can see on the panel is a decent prediction as a very narrow cloud of points on the crossplot, but well number 2 that I mentioned before is not capturing any of the high porosity layers, has a massive dispersion on the crossplot. In terms of attributes, there are 12 attributes that were selected by the process, and all of them, as you can see on the last column of the table, they're all based from seismic inversion. Okay? That's pretty much all it had to calculate. Comparing to the prediction from the advanced workflow, I'm going back and forth, that's the prediction. The red curves adjust better to the wells. Well number 2 now, we can see that the process is actually starting to predict better those thin high porosity sections that the conventional approach failed to capture. Correlation improves to 83%, sorry. And the cross plots in both wells actually show less dispersion, which is a QC for the improved prediction of porosity. In terms of attributes selected by the process, 13 as opposed to 12, so there is consistency there. And if you see again on the last column of the table, all the attributes except for one are actually spectral attributes. So the process clearly prefers the use of those spectral attributes instead of the available seismic and inversion attributes, because it is able to find better matches to the details available in the well data. Applying this to the seismic volume, that's the vertical section of the effective porosity predicted. It is, as I mentioned, it's a carbonate platform. Most of the porosity happens on the upper half of the section. Roughly west to east, kind of like a V-shaped arbitrary line. Well number 3 is actually outside the platform. So that's why you see that massive drop in porosity on that well. Well number 1, this estimation. Well number 2, well number 5, the prediction actually underestimates the porosity values in the section. Or it should be on the wells. This is the results from the advanced workflow using the spectral attributes. And now we can see well number 2. We see those 2 porosity zones that we couldn't see before. So it's original and new results. We were capturing much better those high porosity zones on well number 2, and also an indication of a lower porosity zone on well number 2. An extension of the middle member of porosity to the left side of well number 2 up deep, which is interesting, and some additional high porosity zones away from the well control. Well number 5, that also shows some mispredictions, now is showing a better correlation, not only on the high porosity zones, but we also see a blue layer there that is actually a very low porosity zone that seismically we're starting to showing now. Okay? We can identify that. And just to highlight a couple of things, I'm pointing out different parts of the section. As I mentioned, that up deep event away from well number 2 that was not present in the conventional workflow prediction. The middle section, those high porosity zones, they were interpretable in the previous result, but they look much clearer in here. And I'm also pointing out a couple of thinner, relatively high porosity intervals between wells 4 and 5 on a deeper section of the column. Okay. To finalize, the integration of spectral attributes in the supervised machine learning process shows that the algorithm actually prefers to select spectral attributes over seismic and inversion results in the prediction process. The proposed workflow actually increases the correlation coefficient. The conventional workflow gave a correlation of 73%. We're increasing that correlation to 82%. But not only that, the prediction result with the spectral attributes also gives better resolution. So we see thinner layers, we see better lateral continuities and discontinuities, we see better stratigraphic information in the section, and we also see better match to the actual porosity values in the well data. And last but not least, the display of the vertical sections for both prediction processes show consistency. So the overall distribution of the porosities is actually consistent between the two prediction results. It is consistent with the geological setting and help us identify with the new workflow, identify thin, high, and low porosity zones, which are both important to know the limits of the reservoir, and also help us identify potential prospective high porosity zones away from the well control. So thank you very much.
Thank you, Gabriel. We have our last speaker, and that is Professor Raymond Johnson. Raymond is the GM of Technical Services at Novus Fuels. He's a professor of well engineering and production technology at the University of Queensland, and he's an adjunct professor at the University of Southern Queensland. And Ray's going to talk to us today about recent technologies to improve low permeability coal bed methane production outcomes and coal methane pre-drainage.
Thank you. I'd like to really emphasize that a lot of the benefits of this came from coal mine operators who have no choice but to get the gas out of their reservoirs. Low perm coals is not the flavor of the day, but it is your future. You don't have the low hanging fruit anymore. And when we talk about low perm coals, they have different behavior because they are low perm, they are gas charged, and they're often under stress. So net effective stress plays a major role in them. So I'm going to breeze through this. Everything is well referenced. If you can find this abstract, or you can go to a 2024 ERTEC paper and a 2025 ADAPEC paper, and they're summarized some of the techniques in there. So going forward. So I'm going to go briefly through this because we're running a little bit behind time. So conventional drilling and fracturing methods almost often fail to deliver commercial results for either mine gas drainage in low perm environments or areas with pressure dependent permeability, or where you need to maintain conductivity, you have limited drainage area, and problems with high methane emissions. Global pressures to reduce methane emissions is needing, so CMM is driving a lot of technology that we can use in the CBM industry. We propose an integrated framework to reduce the uncertainty and guide your early decisions on development strategies. This is an integrated technical workflow. It's not a religious belief system like North America has really evolved outwardly when we talk about CBM developments. It combines geosciences, engineering, and advanced stimulation. We use diagnostic fracture injection testing to define reservoir parameters, stress parameters, and their interrelationship between the two, which is essential in low permeability coals. We like to enhance the fracture effectiveness and the stimulated reservoir volume. Those are the key to your production and long-term recoveries, including technologies such as indirect hydraulic fracturing with the SIS wells, or what you may call branched wells, or whatever variety you want, as well as microproppants. We have new technologies developing in tight radius drilling that we'll be bringing to the market eventually that would allow you to go laterally and in seam for short radius. What we're trying to do is implement also barriers for mine methane emissions reduction. I'm going to breeze over that today. But the key thing is you've got to define the geological setting of the basin structurally, tectonically, and understand your fault characterization. You need your full coal characterization. The next step is evaluating the geomechanics related to that coal characterization. You can get your drilling and logging data to correlate your seams, evaluate layers, plies that lateral welds can achieve and get more effectively. But it's really incorporating the geomechanics into this that's the essential step to understand how your fractures are going to behave over time. I'm talking about the natural fractures and cleats, because pressure-dependent permeability is your biggest enemy. So this illustrates come from a 2020 paper where we characterize the pressure-dependent permeability as a function of net effective stress with a singular solution of history matching a diagnostic fracture injection test or DFIT. I won't go to it in detail. It's outlined in this paper. Take a picture of that if you want. And what we're looking at here is a singular solution of fracture compressibility that matches what you have in productivity. This takes the guesswork out of your reservoir modeling. Microproppants increase your stimulated reservoir volume. The fractures and cleats are less than 50 microns. Don't expect 100 mesh sand to go there. You can expect fluid to go there during your fracturing process, but unless you put an appropriate size proppant in there, it will not maintain conductivity post the stimulation, and all that conductivity you gain from a stimulated reservoir volume will be lost. There's a number of papers there. There's papers presented in the SBE Journal. There's about 20 years of work in this area that really substantiates a requirement for this. The particles must be less than 50 micron. Now, understanding the stress profile allows you to do a technique known as indirect hydraulic fracturing. You drill the well in and amidst the SIS wells, which aren't producing anymore, by the way, and the pointer doesn't work real well either. But you can see a number of SIS wells in that example up on the right as dark blue lines. The light blue line is the indirect fracture you see in the middle screen. And in that case, it's drilled underneath the seam because we can't put metal in the seam itself. We frack up into the seam and get a simpler fracture. I pumped those jobs with no pad and up to 6 pounds per gallon without any proppant restriction, no screen outs, 23 stages in succession on, we've done now 2 wells, no screen outs at all, and treating it as roughly as I can to get the proppant in there. And what you see is the interconnection to the SIS wells. We have documented that this creates a large stimulated reservoir volume, an envelope. This is where, unlike shale gas, where children hurt the parents, this is where the children save the dysfunctional parents. The parents are not producing. The child saves the parents. So this workflow, which is impossible to read here, is in this paper, the abstract. It's also in this SBE paper. It combines all these steps of the geomechanics, the integrated reservoir modeling, tying all this together in a framework that you can design, execute, and evaluate your frac treatments or your productivity and maximize your stimulated reservoir volume. Tight radius drilling was deployed early in the mining industry. Its scale is very difficult to deploy because it requires 9 5/8 borehole to start with and then work out from there. We're monetizing this and miniaturizing it to where it can be deployable on a larger scale or from smaller well bores. It has the ability to drill multiple wells, multiple short laterals, totally about 1.4 kilometers in length over all the laterals, as you can see in the picture. And I could history match that production in a simulator and match it. Barriers are a way to prevent water influx. We're trialing a barrier application right now on an area where water is so predominant that they can't produce gas. And so to help this, we're going to isolate the water from the productivity and allow the wells to produce. It's basically a dysfunctional frac that damages everything. You get 3 orders of magnitude damage and you reduce the permeability to where it's basically nil. And then you can develop down dip. This, when you use it in a mining situation outside a mine or to prevent mine gas influx, it can reduce the influx into the mine up to about 56%. Down dip gas migrating to the surface is the biggest source of emissions. I know I've gone through this fast, but I'm trying to keep us back to the end of time. And everything here, like I said, is referenced and well referenced, and my papers are a really good cure for insomnia. So I encourage you to grab one if you suffer from sleep insomnia and read away. But low permeability wells require stimulation. Permeability and PDP definition remain the key challenges. DFITs, diagnostic fracture injection tests, are not just going and pumping in there and see what happens and look for closure. It's a well-designed test, if you do it properly, that gathers key stress and key reservoir data. And it can also help you understand your pressure-dependent permeability behavior. In areas of poor PDP or high where you end up with poor fracture effectiveness, improving the SIV either through indirect hydraulic fracturing or microproppants can aid your drainage. There's not a lot of coal miners in the room, so I'll leave this to be left behind on pre-drainage. But there's a lot of benefit with mine drainage, managing drainage, and beneficial use of gas for economic opportunities. So, continue integrating DFIT, pressure-dependent reservoir simulators. This is in the, no, I'm sorry for the acronym not being defined here. And after closure analysis workflows from your DFIT to better constrain your permeability and pressure-dependent permeability effects. There are further laboratory studies needed under microprop and under fracture conditions, but the application of it has had its first case where we produce gas immediately after the frac treatment the next day from a coal at 30, from a series of coals, I should say, 4 of them at 3,800 meters. So using microproppants can dramatically change your outcome on coal bed methane, and it is commercially available now. So for CMM environments, we need barrier technology trials. If you want to do it for water control, it's very useful there. And there's also a lot of, you're in the CMM industry, there's a lot of, I thought there might be a coal miner here, but I don't think there is. But there's a lot of use in selling for power flaring or diesel displacement to reduce your emissions. And that's going to be a big thing going forward under the Global Methane Initiative. So I'd like to recognize the support of Novus in allowing me to prepare the paper and attend this presentation. But a lot of this underlying research was funded by the University of Queensland, the Gas and Energy Transition Center, and its industry members, Aero Energy, APLNG, and Santos. And there's been nearly 20 years of work done by ourselves at UQ and the Adelaide School of Petroleum in this area. I encourage you to read my RTEC 2024 paper on 20 years of technology. So with that, I'll leave it to you.
Great. Thank you, Raymond. And that closes this session. Thank you.